that I decided to make it a little bit more specific. So I'm interested in mathematical modeling and simulation in close interaction with experiments to understand a variety of mechanical systems, and recently biological interfaces in animals, going from epithelial sheets to cytoskeletal and adhesion complexes around the cell envelope down to the bilayer membrane. But you know, in the interest of concreteness, and because it's a topic I'm very excited about and is developing, I'm going to talk about the epithelial mechanics, so at this scale, at the scale of these cell monolayers, revealed by 3D sheets of cells of controlled size and shape. And this is work by Ernest Latorre, who's a PhD student that is co-advised by me and Xavier Pat, where in his lab, most experiments that I will be showing were performed, and also by Sohan Kale, which is a postdoc in my group, and I'll be presenting a little bit of work of Alejandro Torres regarding the cell cortex. All right, so let me introduce epithelial sheets, although they've already been mentioned in the meeting. So this doesn't seem to work. Otherwise, I use my finger. Yeah, so epithelial cell monolayers are extremely simple tissues. So these are cohesive sheets of cells that are attached to each other and often attached to a matrix, and which delimit most free surfaces in our body. So here you have a side view of an epithelium in an actual tissue, and this is a culture one. So this is a side view where you see these columnar cells. They can take various shapes, and this is the junctional network seen from the top that shows how cohesive and dense this tissue is. So these sheets are remarkable active and multifunctional material interfaces. So they protect us from many things, from pathogens, from desiccation. They control transport across these interfaces in many of our organs. They are also able to self-heal if damaged. So this is an in vitro experiment that mimics a microscale wound healing. They can remodel in 2 dimensions and in 3 dimensions. And remarkably, they can do this while operating under very large amounts of stretch, either in our adult life, so every time we breathe or we move around, or also during development. Okay, so this movie didn't play, but in development there are many events where these monolayers are severely deformed. So the main question that behind this talk, so this is working, is to understand the mechanical properties of this 2-dimensional material as it is stretched. Okay, so this is the basic question. And a number of experiments have examined this issue. For instance, in the group of Guillaume Charas here in the UK, they were able to suspend monolayers devoid of matrix between 2 rods and stretch them, and then they could measure okay, it's a mess. So they could measure the extension stress relation, and they could see how this material was able to recover the deformation elastically. They also observed a creep-like behavior. So in a work in which I was involved, monolayers were cultured on top of hydrogels with fluorescent beads on top of a deformable membrane, and by stretching the membrane, okay, this is not working. Yeah, so by stretching the underlying membrane, you could understand the mechanics of this epithelial sheet. In particular, by tracking the deformation of these beads, you could compute the tractions that these cells were exerting on the substrate, and there you could, from these tractions, back up the tension building up in the tissue. And this is a control, because this material has a tension, a spontaneous tension caused by the activity of the cells. But when you stretch, you have a high tension that relaxes over time. You unstretch, there's a deep in tension that recovers over time. Okay, so there's an interesting time-dependent rheological behavior of this material. Another aspect that I'm not going to discuss, but which was touched upon in these 2 works, is epithelial fracture. In particular, in the work where I was involved, there was an interesting hydraulic fracture caused by the hydrogel pressure building up upon compression, but this is a different story. So we want to understand, and now I'm going to introduce, where do these mechanical properties, this stress extension relation, these time-dependent rheological properties come from? So they come from, so it's believed that they come dominantly as a result of the mechanics of the actin cortex. Okay, so this is a fluorescent image where you see the actin cytoskeleton in an epithelial cell sheet, and so the actin cytoskeleton in epithelial cells organizes as a cell cortex, which is a thin layer of an actin network underlying the plasma membrane, which has a number of components. So it's very thin compared to the size of the cell, so you can think of it as a quasi-two-dimensional object. And there are molecular motors that actin filaments that are myosin motors that are able to create an active tension in this network. In principle, you can think that you will have different tensions in different places in your cortex, and this will drive, on the one side, flows within for a fixed shape. It will create like tangential flows of this material, and it will also lead to shape changes. Okay, and this interplay between tangential flows, shape changes as a function of tension gradients is mediated by curvature, and I will not have time to touch upon this. And then this is also a material that is undergoing turnover. At scales of 1 minute, there's been a complete turnover of the cortex, and therefore at time scales longer than a minute, this network will behave like a fluid, largely like a viscous and active fluid. Okay, so we have this active viscoelastic fluid, elastic because if you probe it at fast scales it will behave elastically, and it's undergoing constant turnover. All right, so this actin cortex is responsible for many mechanical functions of cells. It's involved in cell division. It's involved also in a number of motility modes in which you have a polarization of an actin flows, which is similar to what Davide mentioned this morning. And so let me skip this slide. This was just to make the point that in the presence of curvature, you have this intimate coupling between tangential flows and shape changes. So let me introduce a model that we've been looking at, and others as well, a simple model that includes these ingredients. So this is a continuum model in which you have a number of ingredients. One of them is the cortex density. So we're going to assume that the thickness or the density of this network can change in space and time. Then this is an interfacial fluid, so there is some kind of cortex viscosity that will be proportional to the thickness of the cortex, and this is the rate of deformation tensor that involves both tangential flows and the shape changes in the presence of curvature. You will also have this active tension that we will assume is proportional to the cortex density. So the more material, the more actomyosin gel you have, the bigger this active tension. And then you have this turnover that will be modeled with a polymerization rate that is constant as polymerization happens at the membrane, and depolymerization rate that is proportional to the amount of cortex, and then you have a mass conservation. So you put all these things together, and then you can understand the self-sustained polarization of cortices, which has been observed in experiments. So this experimental move is not playing, and that can result in cell locomotion and also aspects of cell division. But let's go back to the mechanics of epithelial sheets. So this is this active gel, able of performing active forces. So now if you take this mass conservation and you consider that you are in quasi-equilibrium, then all these things are zero, and then you can, from this equation, you can compute the cortex density as a function of these two polymerization and depolymerization rates, and therefore the active stress will be constant, essentially. Okay, So within this simple framework to understand the epithelial mechanics and the mechanics of the cortex, you can understand that the tension in this active interface will be constant, and then the system looks very much like a foam. And in fact, this is the motivation for a family of models that are called vertex models to understand the mechanics of epithelial cells, epithelial layers, in which the cells are modeled as polygons, and then you write down some kind of work function, energy, that will be, you'll have like constant tensions that are multiplying the apicobasal area or the lateral area. And then you also have another ingredient, which is volume regulation. So on occasions, these cells maintain volume. And also the adhesion tension that I'm not mentioning, you put also these junctional rearrangements, and this is a powerful tool to understand epithelial mechanics. Now, much of the current understanding has been based on two-dimensional measurements. However, most epithelia in nature and also in biomimetic systems involves curved three-dimensional shapes that are often enclosing a pressurized lumen. And then, so this is a motivation to propose a new experimental setup. And then in the stretch experiments that I showed earlier, you only achieve moderate deformation. So these are rather large, but they are smaller than many of the stretches that are undergone by real tissues. So to address this, Ernest and Laura got inspiration in an event, a very simple event of epithelial morphogenesis that are called epithelial domes, that occur spontaneously in epithelial cell sheets adherent on an impermeable substrate. And in this case, what happens is that you have so these are rods covered by an epithelial layer. So you see this dome from the top and this dome from the side. What happens is that these cells, these MDCK cells, are pumping ions, and then this is creating a pressure that is able to delaminate this layer and create this dome or blister. Okay. So to understand this more quantitatively and in a much more controlled way, what Ernest and Laura did was to have a soft substrate on top of which they would pattern this fibronectin adhesive protein on top that cells need to adhere to this substrate. And then they will seed epithelial cells on top of this substrate. They will invade first the adherent region, then over time they will start invading the non-adherent region, finally creating a confluent monolayer, and then over time, in a very systematic way, these domes would form. And this would allow Ernest and Laura to create arrays, massive arrays of domes of controlled shape and size. So here you have many of them. These are outside of the pattern. These form spontaneously. These are cross-sections of these structures that one finds. Now, you can use this system to understand the epithelial mechanics in the following way. So you have this pressurized cavity, and this is going to deform this soft PDMS substrate. So what you can do now is to kill the cells and then compare the position of these fluorescent beads before and after the cells were there. And by doing this, you can infer the forces that these cells were exerting on the substrate. If you do that, you find that the arrows are the tractions on the plane, the colors or these arrows are the tractions out of the plane, and you find that the traction here is constant and downwards, consistent with the fact that it's a pressurized cavity. But what's nice about it is that then you can measure the radius of this spherical dome, which is very close to being a sphere, and then you can use Laplace's law and get the tension in the tissue. Now, what's interesting is that these domes are highly dynamical. So they are not static structures, they are inflating and deflating all the time. Okay? So if you run this experiment over a number of hours, you end up getting lots of data. Lots of data about the tension as a function of the nominal stretch, which is the area of this dome compared to the area of the footprint of this dome. Okay? And then you can build this kind of tension-strain relation up to strains that are of 300%. Okay, so you stretch very, very much this material.
How many epithelial cells sit in the arch?
So on total, 100 maybe.
I mean, that's over the area. When I'm looking at this kind of in cross section. So that's 10. If you say it's
12, 10, yeah, something like this.
Okay.
So the point I want to make about this figure is better made if I do this. Okay, so the strain is really large, and the tension initially increases, but then it's pretty much constant. Okay, so there is some kind of tensional buffering mechanism that is limiting the amount of tension that these cells are able to, that this tissue is able to perform. So you're taking this material, imagine any material that you know about, you stretch it 4 times, and then you get this tensional plateau, which is something quite remarkable. Okay, so a number of mechanisms have been proposed to explain, tensional homeostasis in cells. One of them would be that there is a rapid cell division. So you stretch, and then you have more material being accreted, and this is why you can control the tension. However, in the experiments, the stretch is accommodated by cellular stretch without any significant network rearrangement. Okay, so really here you're stretching these cells up to very large amounts. So, so maybe I've just given you the, made you, awaken your interest in the problem. I will not be able to answer fully what's going on here, but if you go back to these epithelial vertex models, okay, and then you see what would be the tension that this model would predict. You can write down an analytical expression in which you have this dependence on the applied aerial strain, and then this predicts, in fact, that there is a tensional plateau. Okay, so these very simple vertex models do predict that you have this tensional plateau. However, this is not the end of the story, because if you look at the actual cell deformations, you have a huge heterogeneity in strain. So some cells are increasing their area tenfold, strains of 1,000%, while others are deforming less than the applied overall strain. So you have a huge strain heterogeneity. And you can see this in this movie of a deflation event. And this is not captured by this vertex model that I was mentioning before. So to make the story short, we had a hypothesis that was that because the active density is smaller on stretched cells, and this you can easily understand in a model that accounts for the limited availability of cytoskeletal components. So you're stretching it a lot, so the cortex increases the area by 2-3-fold. You run out of actin, then the density will go down with strain, a hypothesis that was confirmed by experimental observations. And then this will predict a softening behavior of this material. Then you put this in the model, and still it doesn't work, because you know that if you have softening, you have strain localization. Okay, so then you have to invoke the fact that it's not only the cortex, there are other elements in the cell that can provide mechanical resistance under very large deformations, such as intermediate filaments, the depletion of the membrane reservoir. And then if you introduce this additional restiffening under large stretches, you do recover this phenomenology in which cells are popping into a large strain phase. Okay, so to summarize, thanks to this new method to design epithelial domes, we have observed very large recoverable deformations, a stress plateau, and the coexistence of these superstretched and barely stretched cells. And this can be explained by this generic vertex model that exhibits softening due to depletion of cortical components, restiffening, and in fact, if you look at the energy landscape of this model, you have this two-well structure that appears under tension. You have this progressive phase transformation under stress. So this is just an instance of superelasticity, mechanical behavior that is observed in other kinds of materials. And this would be a mechanism by which epithelial cells can sustain huge deformations by maintaining, a controlled tension. And I leave it here because I don't have time, but we're trying to understand what are the implications of this observation. Okay, thank you.
Thank you. While the next speaker gets set up, take a question or two. I have one. So what sets the length scale of these delaminated regions, the 100 cells?
Okay, so
is that built into the model, for example?
no. So in this experimental system where we have patterns of non-adhering regions, if they are too large, the cells will not invade this pattern, and it wouldn't work. And if they are too small, so you get shallow domes. So in the spontaneously created domes, it's a balance of the pumping rate, the hydraulic resistance, and adhesion and tension in the tissue. So you can understand why they have a characteristic size.